Operations with complex numbers. I know we've talked about what complex numbers are, we've talked about format, we've talked about really what creates the need for them, which is the idea that we don't have anything else to do with the square roots of negative numbers, more specifically the square root of -1. And so we defined that imaginary unit. Things we need to be capable of: finding the absolute value, addition and subtraction, multiplication, and division, which is really not a whole lot more than rationalizing the denominator, because if we remember, I is the square root of -1, we're not going to be allowed to have i's in the denominator of our fractions. For starters, we work in the complex plane when we're trying to talk about complex numbers, where the horizontal axis is real, the vertical axis is imaginary. The point AB would represent the number a plus bi. 3 minus 2i, for the sake of our example, gets plotted in the fourth quadrant. Now, we do that because we move 3 units along the real axis, 2 units down along the imaginary axis, landing on that point. The absolute value of a plus bi. Well, absolute value is distance to 0. In this case, it's going to be the distance to the origin, represented by the red line. If you look, that's a right triangle. So if I want to find the absolute value of a plus bi, Pythagorean theorem says it's going to be the square root of a squared plus b squared. If I calculate that quickly, plug in what I know for a and for b, the I is not there anywhere because it was the b value that dictated distance along the imaginary axis. And so the absolute value of 3 minus 2i is the square root of 13. Addition and subtraction. Things don't change much. We add the real parts, we add the imaginary parts, we move on. What it amounts to is combined like terms. So for example, if I have 2 plus 3i plus 4 minus 5i, the 2 and the 4, those are my real parts. 3i and negative 5i, those are my imaginary parts. Lumping them together, 2 plus 4, 3i minus 5i, I get 6 minus 2i, all said and done. Subtraction doesn't work a whole lot differently. I need to acknowledge the fact that I'm subtracting. So when I combine those like terms, I'll subtract. 3 minus 10, negative 7i minus 4i, I get negative 7 minus 11i. Addition and subtraction, we can do this. Multiplication. Now, the only thing that's really changed is that we know I squared is equal to -1. So we'll use that as we multiply. If we multiply 3 times 6i, that isn't really any different than monomial times monomial when we weren't working with complex numbers. 3 times 6 is 18, I get 18i. 6i times -2i. Well, now I've got imaginary times imaginary. I'll multiply 6 times -2, I'll multiply I times I, resulting in -12i squared, but since I squared is -1, I can replace it with -1. -12 times -1, positive 12 is the actual product. 2i times 3 plus 4i. Now I've got monomial times binomial. I distribute. We know these properties. We know these mechanics. We just need to work with the I values that result. I get 6i plus 8i squared, again acknowledging that I squared is -1. 6i plus 8 times -1. There's the real part just surfaced. It was actually the second term, so -8 plus 6i is the final answer. Last but certainly not least, 2 minus 3i times 4 plus 5i. We've got binomial times binomial. This is where you're going to say, I need to FOIL. It's the distributive property. It comes in 4 pieces, each of them resulting from one of those arrows. We clean things up a little. Just like anything else, the middle terms are going to be combinable. In this case, they create our imaginary part. So 8 plus 10i minus 12i minus 15i squared. 10 minus 12 is -2. And then I squared is -1, so 8 minus 15 times -1, or plus 15, is 23. Division. Division is about rationalizing the denominator. Division is about acknowledging that I is really a radical. It's the square root of -1, which means now I can't allow I to be a part of a denominator. It's easy when the denominator is a monomial. 4 minus 6i over 2i In order to create the situation where there's no more i's, I want to create an I squared. To create an I squared, I'll multiply by I over I. It's just 1. I'm not changing anything about the value of my expression. I'm only going to change the way it looks. Distribute in the numerator, 4i minus 6i squared. Well, at this point, we should know that I squared is -1, so -6 times -1 plus 4i, and 2 times -1 in the denominator. This is technically value-wise the same, but because we're working with complex numbers, we want to represent it in a plus bi form. We'll divide everything by -2. -3 minus 2i, final answer. Now, the struggle comes when we have a full complex number with both a real part and an imaginary part in our denominator, when there's a binomial down there. We have to work with things slightly differently in order to make sure that we accomplish the task. So if I have 3 minus 2i divided by 5 plus I, our trick before was to multiply by I over I. That's not going to work. If we think about what happens when we distribute in the denominator, 5 plus I times I, great, we got an I squared. But unfortunately, we also landed ourselves another I. We still have an imaginary part to our denominator. Here's where the complex conjugate comes in. Conjugate pairs are complex numbers that result in real numbers when you multiply them. Format-wise, it's a plus bi, a minus bi. Now, we've seen things formatted like this before. These are the factors when we factor the difference of squares. It's the product of a sum and a difference. So thinking about what happens here, when I distribute that, the middle terms end up canceling each other out. Those middle terms are what create the imaginary part when we multiply. So all I'm left with is a squared plus b squared, after I squared being acknowledged to be -1 plays in, which is just a real number. So choice, we're going to multiply by 5 minus I over 5 minus I. It's a creative use of the value of 1. Distribute the numerator, distribute the denominator, acknowledge that those middle terms in the denominator fall out, means we chose right, and we start cleaning things up. Combine our imaginary parts, acknowledge that I squared is -1. We get 13 minus 13i over 26, right? 15 minus 12, and 25 plus 1. Putting it in a plus bi form, 1/2 minus 1/2 I. That's it for operations.